Welcome back, Design Junkies, to Mechanical Engineering Made Simple. We're embarking on a deep dive today into really the foundations of motion analysis, the kinematics and dynamics of a particle. If you've ever wondered how engineers track objects like missiles, or maybe design high-speed centrifuges, or, model systems where something spins and slides at the same time, this is where that critical analysis really starts. Our source material takes us straight into advanced dynamics, focusing on how we apply geometry and calculus when motion is genuinely curved and, well, three-dimensional.
Right. And the mission here really is to navigate these coordinate systems that actually move with the object. We need to go far beyond the standard fixed X, Y, and Z axes that, we all learned first. We need to simplify the crucial and, often intimidating equations for velocity and acceleration in these complex curvilinear systems. By the end of this deep dive, you'll understand why picking the right set of coordinates is, well, often half the battle in solving a complex engineering problem. And we'll prove it with a really powerful practical example involving a spinning rod later on.
Okay, sounds good. Let's unpack this then, starting with the absolute fundamental building block for this whole branch of mechanics, the particle. In dynamics, how do we actually define a particle? It's defined conceptually as a material point, without dimensions but containing a definite quantity of matter.
Yeah, and what's fascinating here is why engineers rely on this idea. I mean, it's a physically impossible dimensionless point, right? We use it because when the size of a massive body, think a planet or a star, is extremely small compared with its overall range of motion, its trajectory, we can actually model it very accurately as a particle. But don't think about astronomical mechanics. A planet is huge, sure, but relative to its orbit around a star or its path through the galaxy, it's tiny. Modeling it as a particle is precise and efficient. This simplification lets us tackle these immensely complex trajectories.
Okay, so it's a simplification tool. And the standard approach, the baseline for describing motion, especially straight line motion, is simple Cartesian coordinates, x, y, z. We all know Cartesian works great for straight lines, mainly because its unit vectors a, j, and k are fixed in space. They don't change direction.
Exactly. But the moment the path curves, those fixed axes kind of fail us, or at least they become computationally messy, because the particle's movement is constantly misaligned with them. If we want to analyze motion that involves rotation or radial change like that block sliding on a spinning disk you mentioned, we really need a system where the axes themselves move with the particle.
Okay, that makes sense. Which brings us pretty directly to our most useful curvilinear system for 3D analysis, I'd say, cylindrical coordinates. This system seems perfect for motion that mostly happens in a plane but might also move vertically, like maybe a satellite in a decaying orbit, or some manufacturing process feeding material outward while spinning.
That's right. This system is defined by three components. We use rho, which is the radial projection onto the xy plane, sort of the distance from the z-axis if you look from above. Then there's phi, the angle in that xy plane, measured from the x-axis usually. And finally, z, which is just a standard height component, same as in Cartesian. So the position vector is written as r equals rho arrow plus zk. But here's the crucial part. The unit vectors arrow and fe are no longer fixed like I and j were. They actually change direction as the particle moves and rotates. That's the source of all the interesting complexity, mathematically speaking.
Ah, right. That dynamic change in the unit vectors. It means we can't just take simple time derivatives like we did with Cartesian motion to get velocity and acceleration. So when we calculate velocity, we end up with a vector expression. Let's break that down. Conceptually, what are the physical components of the velocity vector v in this cylindrical system?
Okay, velocity in this system splits nicely into three pretty easily recognizable physical actions. First, you have the radial velocity component. That's simply the speed at which the particle is moving directly away from, or maybe toward, the central z-axis. We can describe this as the rate of change of the radial distance, d or o, over dt.
Okay, outward or inward speed. Then there's the rotation part.
Yes, that's the tangential speed purely due to the rotation. It's calculated as rho multiplied by the rate of change of the angle phi d phi over dt, which is simply the radius times the angular speed, omega. Makes sense. And finally, the third component is just the vertical speed, dtz over dt, same as before.
So velocity seems pretty straightforward once you understand the physical meaning of each term. dr rho, d set, dz, d, radial, tangential, vertical. Got it. But you mentioned the complexity comes in with acceleration. This is where the physics can surprise you, right? When we take the second derivative. This is where those changing unit vectors really make their presence felt, creating components that just don't exist in simple straight line motion.
Indeed. This is where it gets really interesting. In the final full acceleration expression, we see a radial component, the part along arrow, that actually has two terms. The first term is what you might expect. The second time derivative of rho d squared, rho o dt squared. That's just the change in radial velocity.
Yeah.
But the second term is minus rho multiplied by the angular velocity squared. So minus rho times d phi dt squared.
Hold on, I recognize that second term, minus rho omega squared. That looks like the inward centripetal acceleration, doesn't it? That's the term responsible for keeping the particle curving inward instead of just flying off in a straight line tangential to the curve.
Precisely. That's the pull toward the center needed for circular motion, or any curved motion in that plane. But the tangential direction, the e phi direction, also contains two terms, and one of them is hugely significant, especially in engineering design. It's called the Coriolis term. This term is calculated as 2 multiplied by the radial speed, d rho dt, multiplied by the angular velocity, d phi dt. So 2 times d rho dt times d.
Wait a second. So if I'm, say, building a robot arm that's extending outward while its base is rotating, I have to account for a side acceleration, and therefore a side force. A force that doesn't feel intuitive because it relies on the multiplication of 2 completely independent motions moving outwards and spinning.
That is probably the single biggest design risk captured by this acceleration equation that engineers sometimes overlook, especially early on. The Coriolis acceleration exists purely because you have motion in the radial direction and rotation happening simultaneously. It's an interaction term. If either the radial speed is 0 or the angular speed is 0, that Coriolis term just vanishes. Poof. But it's the interaction between the two that generates this often unexpected side force. If you're designing high-speed machinery like turbines or pumps or even certain types of amusement park rides, this interaction force can be absolutely catastrophic if it isn't properly accounted for in the design.
Wow, okay, that's a perfect illustration of why just sticking with Cartesian coordinates wouldn't work here. You'd completely miss that effect unless you did some very complicated projections. Now, just briefly, we should probably mention the big sibling of cylindrical coordinates. Spherical coordinates, this system uses the total radial distance r from the origin, then an angle theta measured down from the positive z-axis, and finally the same angle phi on the xi plane as before. The position vector looks deceptively simple here, doesn't it? It's just r equals r times r.
It looks simple, yeah. But don't let that fool you, because now you're tracking motion in 3 dimensions using 3 unit vectors, air, a theta, and epi. And all 3 of those unit vectors change direction as the particle moves. The result is that the full acceleration equation in spherical coordinates has an incredible 9 separate terms. 9. It includes things like centripetal terms, Coriolis terms related to theta changes, terms related to phi changes. It gets complex fast. This is exactly why engineers always try to use the simplest coordinate system that fits the problem. The complexity really explodes when you track full 3D motion using 2 changing angles and a changing radius simultaneously.
9 terms. Okay, message received. Stick to cylindrical if you can. All right, now that we have the kinematics, the description of motion, let's jump into the kinetics. This is where forces come into the picture. The underlying principle for all particle dynamics is pretty simple, fundamentally. It's Newton's second law, FMA, force equals mass times acceleration. We can use this, along with what we just learned about cylindrical coordinates, to solve a real-world problem involving that tricky Coriolis effect.
Yes, let's set up the scenario properly. Imagine a small block, okay? It's sliding, let's say, frictionlessly for simplicity, along a straight rod. But here's the catch. That rod is itself spinning, rotating in the xy plane around the z-axis like a propeller blade. We need to figure out the side force, let's call it F, that the rod has to exert on the block just to keep it moving along the straight path of the rod while the whole thing spins. It's the force perpendicular to the rod.
Okay, I can visualize that. And we're given some key parameters from our source material to work with. The mass of the block, Nr is 130 slug. Remember, slug is the imperial unit of mass. The block is sliding outward along the rod at a constant radial velocity, so that's a dray of 30 feet per second. And the rod itself is spinning with a constant angular velocity, omega, which is diaphet, of 50 radians per second. Constant speeds, both radially and angularly.
Right. Now, we can try to solve this using F equal ma directly. We plug in the full cylindrical acceleration vector we discussed with the centripetal and Coriolis terms. But honestly, that gets pretty messy with substituting all the components. There's often a much cleaner approach, especially for problems involving rotation, using the angular momentum principle.
Ah, excellent idea, the angular momentum principle. This states that the net moment applied to the particle, m, must equal the rate of change of its angular momentum, h, over time. So m equals dh dt. And angular momentum h itself is defined as the cross product of the position vector r and the linear momentum, which is m times v, so h equals r cross mv.
Exactly. And in our scenario, this block sliding on a rotating rod, things simplify nicely in cylindrical coordinates. The side force F, exerted by the rod on the block, creates a rotational moment, m acting perpendicular to the rod, in the z direction, or k direction. The magnitude is just r times f. When we calculate the angular momentum h of the block about the origin, also in cylindrical coordinates, it simplifies beautifully. Because the velocity components work out just right, h ends up being m times the radial distance r squared, multiplied by the angular velocity omega. And this angular momentum vector h also points purely in the k direction, perpendicular to the plane of rotation. So hem r squared omega k.
Okay, so the moment m is rfk, and the angular momentum h is mr squared omega k. Now we need the rate of change of angular momentum dh/dt to use m equals dh/dt. Since the mass m and the angular velocity omega are constant in this problem, we only need to differentiate the r squared term with respect to time using the chain rule.
That's right. The time derivative of r squared is 2 times r times dr dt. So dh/dt becomes m times 2r dr dt times omega all times k. Or rearranging slightly, dh/dt equals 2 meter r dr dt omega k.
Perfect. Now we equate the moment m to the rate of change of angular momentum dh/dt. So rfk equals 2 meter r dr dt omega k. We can immediately cancel the unit vector k from both sides. And look, the radial distance r also cancels out from both sides. This leaves us with a really powerful, clean, final relationship for that required side force, F. It's just F equals 2 times m times dr dt times omega.
And look at that equation, F equals 2 meter dr dt omega. This simple, elegant result confirms exactly what we suspected from the acceleration equation. The side force needed to constrain the block to keep it on the rod is entirely driven by the interaction between the radial speed, dr dt, and the angular speed, omega. This force is the macroscopic measurable force resulting directly from that microscopic Coriolis acceleration term we identified earlier, 2 d rho to d, d rho d. It's the same thing, just expressed as a force via Fmi.
Amazing how it connects like that. Okay, now for the calculation. Let's plug in the numbers we were given. Mass m equals 130 slug, radial velocity dr 30 feet per second, angular velocity omega equals 50 radians per second. So F equals 2 times 130 slug times 30 feet times 50 rads.
And the math is pretty easy here. The 130 and the 30 cancel each other out perfectly, leaving just F equals 2 times 50. The result is F 100. And the units work out to pounds force, pound BF.
100 pounds force. For a block with a mass of only 130 slug, that's a tiny fraction of a pound of mass, maybe around half an ounce, yet it requires a massive side force of 100 pounds just to stay on that spinning rod while sliding outward. Wow. Imagine if an engineer designed this system and, say, only calculated the centripetal force needed to keep it moving in a circle at a fixed radius. They would completely miss this huge 100-pound Coriolis-driven side load. The rod connection, or whatever mechanism holds the block, would probably just shear off instantly. This analysis is literally the difference between a stable design and catastrophic failure in many high-speed applications.
It's absolutely not a trivial force. And the design takeaway is crystal clear. In any system where you have a body moving radially or changing its distance from the center of rotation while it is rotating, you absolutely must account for this coupling term. Whether you find it using the full acceleration vector or, like we did, using the angular momentum shortcut, doesn't matter. This rotational dynamics effect, this Coriolis effect, is not just abstract theory. It's a critical physical constraint that has to be managed in the real world.
Okay, let's just quickly recap or unpack what we covered. We started with the basic concept of a particle in dynamics, moved through why we sometimes need curvilinear coordinates, specifically cylindrical because their unit vectors change direction, unlike Cartesian, saw how this leads to extra terms in velocity and especially acceleration, most notably that inward centripetal acceleration, and the really interesting Coriolis acceleration term, 2 d rho d fixity. Then we applied the principle of angular momentum, m equals dh/dt, to a practical example, a block sliding on a rotating rod. And we calculated a very real, surprisingly large 100-pound side force needed just to keep that tiny block on the rod, confirming how vital that Coriolis interaction term is in actual engineering design.
Right. And if we maybe connect this back to the bigger picture of mechanics, this whole kinetic analysis using forces and momentum, it really rests on understanding rates of change. We found that the side force F depended directly on the product of the angular speed omega and the radial speed dr dt, which brings up an interesting point. We assumed constant angular velocity, omega 50 rads, and constant radial velocity, dr dt equals 30 feet, in our example. But what if those weren't constant? What if the rod's rotation was accelerating? Or the block speed along the rod was changing? How would the dynamics change then? What additional forces or moments would we need to consider to maintain or control the block's motion? That's maybe something for you to think about.
Until the next equation, design junkies. Tune in every morning at 11 before 8 a.m.